The black hole. What are we looking at when we visualize one of these things? How does it work? And what is inside the blackness? One of the fun things about black holes is that we have a lot of theories with very few proven answers. So it's pretty hard to say anything objectively wrong about the inner workings of this phenomenon. But we'll still try and be as correct as possible. And regardless of whether this pans out to be true or not, it's still really fun to think about. This is the space race. Okay, let's start off with a brief on how black holes happen in the first place. In essence, these are just blackened corpses of old stars that have imploded on themselves. We know that stars will explode outwards when they die and cause supernovas. Those are cool, but that explosion is just the star shedding its outer layer. The core of the star remains in place and most often will continue to burn what little energy it has left as a neutron star. But on a rare occasion, the core of the star will collapse into a black hole. So how does that happen? Stars are objects in space that are massive enough that the force of their own gravity will ignite nuclear fusion within the core of that object. Most stars are made up mostly of hydrogen atoms. That hydrogen is crushed in the core of the star to create helium, and the byproduct of this fusion is radiation energy that pushes out from the center of the object and acts against the massive force of gravity. The push and pull of gravity and radiation creates a balance that allows the star to remain stable. But if a star gets big enough, the force of its gravity will start to fuse heavier elements than hydrogen. The fusion process will gradually work its way through heavier and heavier gases until it begins to fuse solid elements and eventually reaches iron. But the fusion for iron no longer creates that radiation energy that pushes against gravity. So iron just builds up in the core of the star, and the force of gravity goes through the roof. That leads to a collapse of the core and implosion of the entire star. Not all imploding stars cause black holes. They need to be exceptionally massive to create this effect. That's like the basic level of how this works. The whole theory can get a lot more insane. Technically, you don't need mass to create a black hole. That's just probably the most common way that it occurs in our known universe. But according to Einstein's theory, you could create a black hole out of anything as long as it is either compressed strongly enough or becomes large enough. It's all just a relation of size and density. So, in theory, if you compress a baseball with enough force to start making it become physically smaller, it would eventually reach a small enough size where it actually becomes a black hole. But the other crazy thing is that black holes don't even need density to form. According to the same theory, you could create a black hole from anything as long as you could make it reach a large enough size. So even a balloon full of air with the density of air could become a black hole if it grew large enough. We'd be talking about an unfathomably large balloon, but as long as it could just keep expanding to an infinite degree, it would eventually reach the state of a black hole. Trippy, right? All right, let's move on. Okay, so there are two ways to visualize a black hole. One is with this actual photograph of an actual black hole that was taken 2 years ago. This photo was made possible by combining high-powered telescopes from locations all over the world to create the equivalent of one massive lens aperture that is nearly the size of planet Earth. This insane creation allowed us to see all the way to the center of the M87 galaxy, 55 million light-years from Earth. As far as we can assume, there is probably a supermassive black hole at the center of every galaxy in the universe. This particular one at the center of M87 is 6.5 billion times the mass of our own sun. So if black holes are black and no light can escape, then what are we looking at? The dark center of the object is the event horizon. That's the point of no return. Anything that crosses this horizon vanishes, including light itself. But the event horizon is surrounded by this disk of superheated material that glows incredibly bright, and that's what allows us to pinpoint where the black hole actually is. As amazing as this photo is to look at and imagine, it's not exactly a clear view of what's going on out there. Even with a telescope the size of the Earth, they still had to crop in a whole lot, and that means that there's not a whole lot of resolution left in the actual image. So to get a detailed view of the black hole, we need to switch over to our imagined rendering of what this phenomenon will actually look like. So, like we said, the black hole is surrounded by a rotating mass called the accretion disk. This is kind of similar to the rings of Saturn, just a big, flat plane of matter that is orbiting the black hole. In this case, the disk around the black hole is rotating at about half the speed of light and is superheated to 1 billion degrees, making it incredibly bright. The reason the black hole and its ring look so crazy compared to a planet like Saturn is that the entire accretion disk of the black hole is visible, no matter what angle you view it from. So when we look at this straight-on rendering of the black hole, we can see the front of the disk, the back side of the disk, and the underside all at the same time. The force of gravity from the black hole is altering the path of light as it escapes from the disk and bending it around the core. So what we see around the top of the black hole is the image of the disk's far side, and what we see around the bottom of the black hole is the image of the disk's underside. Then that thin ring of light closer to the center is the photon ring, which is actually multiple distorted images of the accretion disk that is created by light that reflects off of the disk, then gets trapped in orbit around the black hole 2 or 3 times before eventually escaping into the universe. So because of this gravitational lensing effect, we can actually see light that is coming from the other side of the black hole. Not to be confused with the inside of the black hole though. We'll get to the inside. It's like a big trippy space mirror. Okay, so the middle part of the black hole that we are looking at is essentially a shadow. The event horizon is within that shadow, but it doesn't take up the entirety of the black space. The reason being that the gravity of the black hole is so strong that even photons of light that get too close to the event horizon are pulled in and never seen again. So the shadow is about double the actual size of the true center of the black hole. Because light itself is orbiting the center of the black hole, you could actually float outside of the event horizon and look at the back of your own head, because the light reflecting off of your back would make its way around in a circle and reach your eyes. If you could look out into space from the edge of the event horizon, you would actually see your view of the universe narrow to a small circle as the number of angles that light can reach you from slowly diminishes. I don't know what that would look like, but it would be the last thing you ever see before crossing the final frontier into the actual whole part of the black hole. Beyond the event horizon, space and time are operating on a totally different set of rules than what we have in the rest of the universe. It's impossible to say what will be in there. It could be everything or nothing or both all at once, because nothing can escape the event horizon. Once inside, there is only one direction that you can possibly move, and that's towards the center. No matter which direction you turn, all movements only take you closer to the middle, and in the middle lies the singularity. The singularity is most likely the point where all matter that has ever entered the black hole is crushed together into one thing that is both infinitely small and infinitely dense at the same time. Doesn't really make any sense, does it? We can't explain the process, but yet we are pretty sure that it is happening, and that's what makes black holes so friggin' neat. Okay, so everything that we just said about getting pulled through the event horizon, never to be seen again, and crushed into a singularity is all inevitable because even light cannot escape this force. But what if you could travel faster than light? Physically, it is impossible to do, but just for fun, let's imagine what might happen if you could. In theory, if you could activate a faster than light propulsion engine from within the event horizon, you should be able to go back out the way that you came, and that would have some crazy implications on your relation to time as we know it. Or, on the reverse, anyone watching you enter the black hole from the outside would see you gradually slow down and stop, then fade away. That would give the impression that light is traveling more slowly as you move down into the black hole, but since light must always move at the same speed everywhere in the universe, then time itself has to give way and move more slowly to accommodate the speed of light. Or something like that. I don't know. Go read a Stephen Hawking book if you want a legit explanation. But the point is that when you emerge from the black hole, the flow of time in the outside universe will have been moving faster than it was for you on the inside. So, according to that theory, dipping into a black hole coming back out again would move you into the future. You might be able to skip over years, decades, centuries, or even more on Earth just by hanging out in a black hole for a little while. Now here is one more crazy thought for you. If you could move through the center of the black hole faster than the speed of light, then you could avoid being pulled into the singularity at the middle and actually come out the other side. But what do we find? In theory, if you were to cross the event horizon that runs parallel to the one that you came in through, you would exit the black hole into a parallel universe to the open that you originated from, a mirror universe. And to get there, you would have traveled through something referred to as an Einstein-Rosen bridge, or a wormhole. That leaves us with a lot of interesting questions. Would the parallel universe actually be different from our own? Or would you come out into the same existence that you just exited? Like, if you could travel off the right-hand edge of a map, you would just come back in at the left-hand edge. If we know that time moves differently inside a black hole, then what effect does it have on space? Could the wormhole drop you off at some completely new, different place in the universe? It's crazy stuff to think about, right? And I have to say, all of the ideas that we covered here are based on the model of a stationary black hole that does not move or spin. In reality, most or all black holes probably do spin, but that would throw in a bunch of crazy variables that would really take this video off the rails and make everything a little bit less fun to imagine. So this is the simple explanation we're going for here.